After a month and a half of painstaking adjustments, the James Webb Space Telescope has formed a perfect image of a star for the very first time. What started as 18 random smudges of light have now transformed into an image of a star with a deep field of distant galaxies in the background. And if that weren't cool enough, we even got to see an actual selfie image of Webb's primary mirrors, fully illuminated by starlight for the very first time. Okay, I have to admit, I had some mixed feelings about this image when I first saw it because I had just finished a video about how the mirror alignment process was going, and right before I was about to hit the publish button, NASA released their update and made me look like a chump. But who cares? I mean, this is an amazing image. It's not the prettiest image Webb will ever take, or even the most scientifically interesting one. But it is the highest resolution infrared image ever taken by a single telescope. The star doesn't have a proper name or anything because it's about 100 times fainter than what the unaided eye can see. But it was one of several stars that were chosen for their brightness and relative isolation from other stars. This image was taken with Webb's near-infrared camera at a wavelength of 2 microns. And that's outside the range of visible light, so the red color was added by the optical team to measure the contrast in the image. The first thing that really stands out are those large diffraction spikes. Diffraction is the tendency of light waves to bend around edges, and when this happens, the waves interfere and alternate between canceling and amplifying each other. In most telescopes, light typically diffracts around the flat support struts of the secondary mirror. Each of the strut's flat edges create a perpendicular spike. Most telescopes like Hubble use 4 struts for its secondary mirror, so they generate 4 spikes that overlap each other at the focus. The result is that beautiful Star of Bethlehem effect. Now, since Webb only has 3 support struts for its secondary, they create 6 spikes when focused together. But Webb's mirror is an array of 18 hexagons, each with 6 flat edges. So each segment creates 6 diffraction spikes of their own, and they all converge together at the focus. Notice that in this illustration, the 6 original spikes from the support structures are still visible as well because the struts are 120 degrees apart. Webb's designers overcame this problem somewhat by repositioning the bottom 2 struts to line up with the flat edges of the bottom hexagons. And that allowed 4 of the spikes to align with the rest of the diffraction pattern. The result is technically an 8-sided star, with the horizontal spikes caused by the top strut. And while the spikes are pretty, it's those background galaxies that really got the astrophysics community excited. We've never seen galaxies at such high resolution at infrared wavelengths. Unfortunately, there's no way to get rid of those diffraction spikes because physics. But they only become noticeable when imaging relatively bright compact targets like stars. In practice, Webb won't be used to directly image bright stars like this. But this image does show that Webb's mirrors are now aligned all the way down to the diffraction limit. That means Webb is as focused as well as the laws of physics allow. Now, in one sense, this may be the sharpest image that Webb will technically ever make, and that's because the optical team still have to redistribute that focus a little bit across the entire instrument field of view. But we'll talk about the implications of that in just a moment. For now, though, let's talk about how the optical team turned 18 fuzzy blobs into a perfect image of a star. The process began in early February when Webb was pointed at the star HD 84406 in the constellation of Ursa Major. And this would be the first in a series of stars that Webb would use to align the segments. Ground-based telescopes like Keck use a dedicated instrument called a wavefront sensor. It's specifically designed for the alignment and calibration of its mirror segments. But internal space on board Webb is at a premium, so its near-infrared camera, or NIRCam, was designed to double as Webb's wavefront sensor. As expected, NIRCam found 18 images of the star because Webb's 18 segments were still out of alignment. Each segment is backed by a hexapod of motors as well as a central actuator that can change the radius of curvature. And that allows each segment to be tipped, tilted, rotated, moved around as needed, pushed forward and backward, and even changed its shape by just a little bit until they all form a single monolithic mirror. Before moving the segments, however, the team wanted to make sure that there weren't any anomalies during the initial deployment that would have to be sorted out before aligning anything. So NIRCam took a selfie of Webb's primary mirror. It did this using a special lens called a pupil imaging lens. It works by bringing the image to a focus before it reaches the detector. This causes the light rays to spread out in such a way as to form an image of the entrance pupil instead of an image of the star. Incidentally, you can see this effect yourself in a backyard telescope. You just take the star out of focus all the way to the point where you can see the outline of the primary and secondary mirrors. That's the entrance pupil of the telescope. The first pupil image was taken on February 11. One of the segments was lit up at the time because that was the mirror that was aimed at the star. The next step was determining which of those 18 blobs were made by which mirror segment. And this was done by tipping and tilting each of the segments one at a time. Next, the images were positioned into a hexagonal image array, and that gave the wavefront team an intuitive way of visualizing the segments as they were nudged into alignment. For the subsequent steps, Webb would make a number of adjustments that introduced tiny jitters into the telescope. So the fine guidance sensor was brought online to lock onto one of the images in its field of view. Now, FGS doesn't actually see any of the images that we see here because this image was taken by NIRCam. FGS and the other instruments each look at a different part of the field of view, but the hexagonal pattern is replicated everywhere. So FGS designated one of the sharper images in its field to lock onto. That in turn allowed Webb's fine steering mirror to hold the image nice and steady. The next step was to get each of the images in the array as sharp as possible. And this is accomplished by, believe it or not, taking the telescope out of focus by moving the secondary mirror back by about 400 microns. An algorithm called phase retrieval analyzed the images to work out how far out of alignment the segments were. The segments were then adjusted and the secondary was returned to focus. Now that there were 18 sharp images, the next step was to stack them together in the center. Now, that may seem easy, but it's actually a very tricky process because the images need to be stacked to within a fraction of a pixel. Otherwise, there's no way to do the fine alignments necessary to create a single mirror. So Webb's 18 images were stacked in groups of 6 segments each. By the end of this initial stacking, the image looked a lot more like a star. However, the segments were still acting like 18 individual telescopes because they still weren't yet aligned well enough. In order for the segments to act as a single mirror, they need to be aligned to within the wavelength of light. Now, this is a process called phasing. Phasing is done in 2 major steps of coarse and fine phasing. During coarse phasing, the goal is to reduce what's called the piston error between segments. To measure the piston error, a special mask called a dispersed Hartmann sensor places an array of slits over the pupil. Each slit spans a pair of segment mirrors. The piston error is measured using a technique called dispersed fringe sensing. Here's how it works. Starlight from the 2 segments is dispersed into what is essentially a spectrum. If the piston error between the segments is large, the spectrum takes on a barber pole pattern of fringes. By measuring the angle of the fringes, the piston errors can be determined very accurately. As the pistons are adjusted, the barber poles flatten. After this first round of coarse phasing, a second pupil image was taken to check the alignment, and now all 18 mirror segments were completely lit up by starlight. The image doesn't even look real. It looks like a drawing or something. But if you look closely, you'll notice there are still some fuzzy bits here and there. And that's because the segments were still slightly out of alignment by a few microns. A few microns is a few millionths of a meter. But again, to achieve the expected performance, the mirrors need to be aligned to within a few nanometers or a few billionths of a meter. Another thing to consider is that the secondary mirror's focus was set for just where in the field of view the first image was formed. To measure the error in the surrounding field, the segment images were rearranged into a smaller version of the array. This small array was then moved to different parts of NIRCam's field of view, and then the relative centroids of the patterns were measured at these different locations. These measurements were then used to work out what adjustments were needed to correct the secondary mirror. Incidentally, you may have noticed that there's one image in this smaller array that's deliberately being left out. And that's so the fine guidance sensor has an isolated image to lock onto down in its field of view. By the end of this process, the secondary mirror is aligned and focused. Now the stage is set for fine phasing. During fine phasing, the image must be defocused again to measure and correct any remaining alignment errors. But this time, instead of taking the entire telescope out of focus by moving the secondary, NIRCam uses a set of weak lenses in its pupil and filter wheels that slightly defocus the starlight by very specific amounts. The phase retrieval algorithm then analyzes the image and works out exactly what phasing errors remain. The segments are corrected, this time by making tiny tip and tilt adjustments instead of piston adjustments. After the corrections are made to the segments, a second round of coarse phasing is done to further isolate and reduce any remaining piston errors. And that was followed by additional rounds of fine and coarse phasing. With each round, the point spread function of the star gets tighter and tighter as the segments are adjusted by smaller and smaller amounts. By the final phasing, the segments were moved by just a few nanometers. That's just 1/10,000th the width of a human hair. The result is a diffraction-limited telescope. At least a diffraction-limited telescope as far as NIRCam is concerned. But now the alignment needs to be checked for the other instruments because they're looking at different parts of the field of view. This step is called multi-instrument multi-field alignment, or MIMF. Webb does this by taking 5 defocused images of the star in each of the instrument's fields. And this time the images are defocused by moving the secondary mirror by 100 microns. The phase retrieval algorithm determines what remaining adjustments are needed on the segments and the secondary to fully correct the entire field. These MIMF adjustments will effectively redistribute some of NIRCam's perfect focus across the entire field of view. So technically, NIRCam is going to be ever so slightly reduced from the focus achieved in this image, but by no means will it be reduced enough to impact science, let alone enough to even be noticed. Now, the MIMF alignment is currently in progress as of this filming, and it'll take about another month to complete. Meanwhile, the instruments are continuing to cool to their operational temperatures and will then enter into their final commissioning and then science. Now, let me state that this was just a highly simplified walkthrough of the steps needed to bring Webb into focus. It took the team a better part of 20 years to figure out just how to do this. But optically, the telescope is now performing better than their models predicted it would. But even after Webb is fully operational, it will likely drift out of alignment from time to time. And that's because the telescope's structure will continue to slowly outgas, and that will introduce very tiny changes into the alignments of the mirrors. And that's why fine phasing measurements will be taken every 2 days and analyzed to track the telescope's alignment over time. A small adjustment will likely need to be made every 2 weeks or so. Now, one thing that's pretty clear about this approach to maintenance is that it really underscores the idea that once you have everything set up, it's much easier to make frequent yet tiny adjustments to keep it running than to wait until things get really bad and start all over again. I know that's easier said than done, but the good news is that it's a skill you can master. And that's why I'm so thrilled to have Skillshare support for today's video. Skillshare is an online learning community with thousands of online classes and members across 150 countries who come together to find inspiration and to level up their creative game. This year, I'm making a point of finding ways of creating content more efficiently while still bringing as much value as possible. And that's why I've enjoyed Productivity for Creatives by Thomas Frank, where I'm learning how to build out a system that lets me improve my channel without getting bogged down in so many details. New premium classes are launched each week and are presented ad-free, so there's always something new to discover while staying in the learning zone. If you want to level up your game, the first 1,000 people to use this link will get a 1-month free trial of Skillshare. Please make sure to use the link in the description of this video. As always, I would love to thank my patrons for helping to keep Launchpad Astronomy going, and I'd like to welcome Benjamin M. Day, Ben Degen, Scott Horowitz, Dandeep Jain, Stephen Youngear, Matthew Jackson, Kangarang, Michael Kolb, Phil Light, Leela Nagaligam, Niles M., Richard Pokris, Riva, Jeff Rodman, Joe Rodricks, David Turner, and Holly Vernon. Thank you all so much for helping to keep Launchpad Astronomy going. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.